In this part, we talk about categorical predictors in logistic regression, how we incorporate more than one predictor, the multiple logistic regression, and we talk about polynomial logistic model. Just like in linear regression, when the predictor X is binary, the interpretation of the model simplifies. In this case, what are the interpretations of beta 0 and beta 1? For the hard data, for example, let X be the indicator of the individual male or female. Now, how do we interpret the coefficients in this case? The observed percentage for heart disease for women is 26%, while for men is 55%. Now let's talk about multiple logistic regression. It is simple to illustrate example in logistic regression when there is just one predictor variable. But the approach easily generalized to the situation where there are multiple predictors. A lot of the same details as in linear regression apply to logistic regression too. Interaction can be considered, multicollinearity is a concern, and so is overfitting. How can we estimate a classifier based on logistic regression for the following plot? The challenge here is that we have multiple predictors, x1, x2, and xp. Well, multiple logistic regression is a generalization of the multiple predictors. So now the log odds will be just adding extra predictors to the linear relationship. So beta 0 plus beta 1 x1 plus beta 2 x2, etc. The estimation procedure here is identical to that as before for simple logistic regression. In other words, we write the likelihood function, the negative log likelihood, and minimize it across all parameters beta 0 to beta p using an iterative method like gradient descent. The actual fitting of multiple logistic regression is much easier using software, and of course there's a Python package for that, as the iterative minimization of the negative log likelihood has already been hard-coded. The interpretation of the coefficients in multiple logistic regression is similar to that of a linear regression. The key here is, since there are other predictors in the model, the coefficients beta j is the association between the jth predictor and the response variable, or the log odds scale, but we have to say controlling for the other predictors in the model. So we're trying to attribute the partial effects of each model controlling for the others. Now let's talk about polynomial logistic regression. We saw a 2D plot before, which has two predictors, x1 and x2. A similar one is shown here, but the decision boundary is not linear. We can extend the multiple logistic regression as we did with the polynomial regression. What we did, we transformed the data by adding new predictors, which we call x tilted, and we do the same here. Now x tilted will be 1, x1 tilted, x2 tilted, etc. But now, again as in the linear polynomial regression, any x tilted predictor will represent the polynomial degree. The polynomial logistic regression can be expressed now, again with log odds, as equal to x times beta. Just x now represents any degree of polynomial.